Hello, it's great to be here, albeit remotely, and I look forward to having your questions at the end of this presentation. I've decided to pre-record it, but I will be here for you once we've got to the end of the pre-recording, and look forward to interacting with you. So this is a topic very dear to my heart about current research practices, how they damage science, and how open science offers some solutions. I want to start with the idea of what we think science is. So I think we tend to regard science as a cumulative process where we build on what other people have discovered and take things forward in this sort of way that Isaac Newton talked about, where he memorably said if he'd seen further, it's by standing on the shoulders of giants. And so his discoveries couldn't have happened without prior discoveries which formed the foundation for that. This is the goal. But in practice, I would argue that it's a very common tragedy for early career researchers who end up trying to build on a previous literature that is wrong. And they end up, for example, starting a PhD and thinking, here's an interesting paper with a really exciting result. They want to go forward in that line of work, only to find after 3 or 4 years that they couldn't even reproduce the initial finding. And they start out thinking it's their fault, that they've done something wrong, they're not skilled enough, only to find that then other people say, oh yes, no, that result really doesn't stand up and isn't really credible. And there is a surprising amount of this going on, I would argue. I keep meeting early career researchers who say this happened to them, and we have to ask ourselves why. And of course, it's not just a tragedy for scientists themselves, but it's actually a tragedy for society who funds the science and who depends on the science being accurate. And this has become particularly evident in the age of COVID. So I want to talk about some reasons why I think we have these problems and what I call quasi-cumulative science, where we think we've got strong, firm, credible results when we haven't. And I'll also talk about what I think of as some possible solutions. And the first reason that we have to deal with is publication bias. Publication bias has been known about for many, many years, and it's one source of what I'm going to be talking about as false canonization, the idea that you get a false idea that something is a really firm canonical finding. But this was talked about back in the 1970s. So Greenwald, famous social psychologist, talked about prejudice against the null with this very memorable quote that as it's functioning in at least some areas of behavioural science research, the research publication system may be regarded as a device for systematically generating and propagating anecdotal information. That's a fairly severe statement. And then the very catchy label, the file draw problem, was put forward for the same phenomenon by Rosenthal, who said, well, all researchers have got these file drawers stuffed full of results of things that they never published, usually because they weren't very interesting, things didn't come out as expected. But what this means for the literature is that it gets biased if we only see the things that came out in the way that we had hoped. There was a very nice paper recently published by Nissen and colleagues in eLife, who coined this phrase canonization to describe the situation when a claim is widely accepted as true because there's lots of supporting evidence. And once we get to that point, we stop having to do research on that thing. We take it for granted rather than treating it as a hypothesis that we need to evaluate in the subsequent literature. And if you are interested in Bayes' theory and you think of things in that sort of term, you could say that what canonization means is that you've got a prior belief in the phenomenon that's so strong that it would take overwhelming amounts of counter-evidence to shift to another view. So here are some examples that I just sort of got out of the top of my head. And the interesting thing about this dimension going from green to red is it's going from canonized positively at one level and then canonized negatively at the other level. So on the one at the top, we've got things where we all agree they're true, and you would think it was a bit strange if somebody started trying to run a study to prove it. So the Earth is round, global temperatures are increasing has moved from being perhaps more questionable up into, I think, the canonical area for most of us. And then, much more trivial things, if you like, the idea that caffeine makes you wakeful. There might be people that would say, well, it's all just a mirage, but in general, we would find that something that we would want a lot of evidence to show that it really wasn't true. If we look now, though, at the bottom, we've got things that are equally canonical, really, but they're canonically negative. So astrological forces determine your fate, or extrasensory perception is real, are both things where if somebody started arguing for them, you'd want to see really, really good evidence. Now, this is interesting from the point of view of extrasensory perception because it was a study by a very eminent psychologist, Darrell Bem, who claimed he had evidence for that kind of extrasensory perception that really sparked a lot of interest in many psychologists in the state of our science, because people, rather than believing Bem, most people took the view that something was very, very wrong if he was able to generate evidence for that. And indeed, I think now many people would argue that it was a classic case of p-hacking, which is something I'll come on to talk about. Where most science is happening, of course, is where we don't know whether something's true or not. And I've put this label equipoise, which comes from the clinical literature, to describe a situation when we really don't know if something's true or not, and we have very few prior beliefs about it, such as last year we were in that state regarding hydroxychloroquine and whether it was effective against COVID-19. I think that has now moved down into the red zone because there have been enough studies failing to show that effectiveness. But it sort of went up and down a bit, initially looking as if it might work, and then people finding that they couldn't replicate findings, or that the studies that suggested it worked were of poor quality. So that's where most of the action is. But once something gets canonized, we just build on it rather than evaluating it. And that's where the problems come if we do that canonization too soon. This is what Nissen et al. Argued happens, that we canonize what they call false facts. And they saw publication bias as a major way in which this happens. So the idea is that there is a claim which may in real life be either true or false. So this drug works, it either does or it in fact doesn't. You run an experiment and you either see support or you fail to support it. Now, the support and the failure to support are not absolutely determined by the truth of the situation in many sciences, because we're talking about phenomena that are probabilistic, and so we use statistics to try and decide whether what we've observed is actually compatible with the true state or the false state. But what we observe is not the truth, it's the evidence, and that depends on all these little Greek characters, alpha and beta, which correspond to our alpha level, say 0.05. So you can see here there's an arrow going from the claim being false with level alpha to support, and that means that there's a 5% chance that although the claim is false, you will find supporting evidence. That's the classic type 1 error. And then there's 1 minus alpha that you will fail to support, so you will correctly conclude there's no evidence. And then we've also got beta, which relates to statistical power. So if the claim is true and you get supporting evidence, that's got a probability of 1 minus beta, so that's the power, is 1 minus beta. But you can also fail to support something even though it's true, which is at level beta. So those two terms, alpha and beta, are under the control of the experimenter to a large extent. But then what we have is whether things actually get published. And if you get support for something, it usually is published, and there's a probability P1. But if you fail to get evidence, then it's quite likely it won't get published. So this probability P0 of a null result getting published is much higher than P1 typically. Now what they cleverly did was to then plug this into a simulation and show how this worked out over time with cumulative evidence. But I'll give you just a simple example here, saying that suppose you have a series of experiments testing a treatment to see if it's effective, and you start out from this equipoise position where you think there's a 50-50 chance that it might work. You take alpha 0.05, so the false positive rate should be 1 in 20. You say that power's 0.8, so if there really is an effective treatment, you should see it on 8 out of 10 trials. And then you have 5 studies, and 3 of them are positive and 2 are negative. Now, think that through to yourself. How much confidence would you have on the basis of that series of evidence that the treatment is actually effective? Is it very likely to be ineffective? may be effective but is unclear, or very likely to be effective. Just think about that for a moment or two. So what a lot of people select is option B, but in fact that's pretty strong evidence that the treatment is effective, because you've got an alpha of 0.05, so you should only in 1 on 20 occasions actually find positive evidence if it's not true. And you can actually accumulate evidence, as is shown in this plot here, by computing the log odds of getting this result if there really is a true effect. And when the log odds gets to be more than 4, it means that the true effect is 54 times more likely to be the case than there being no effect. So you've actually climbed up to that level with just these 5 studies, 3 of which showed a positive effect. So you don't always need to find these effects, but if you find enough of them, that's good. How did I do those sums? Just for those of you who are curious. So it's, as I said, it goes very simply from the alpha level, which determines whether or not you see a true effect or a positive result or a null result if the treatment actually is ineffective. So that's how alpha is determined. It relates to if the null hypothesis is true. And then if the treatment really is effective, the power is what determines whether you see a null result or a positive result. And then from those you can say, well, I've observed a positive result. What's the likelihood that it's, what's the odds that there's a true effect behind this? And it would be 0.8 divided by 0.05, which comes to 16. So you get a log odds of 2.77. You just take the log. And then the odds, if you've observed a null result, again, you would say, what's the likelihood of having a true effect then? And it would be 0.2 divided by 0.95. And that's a negative log odds. So you go down below the 0 point, which is the prior log odds when both are equally likely. So each observation adds or subtracts from the previous one. Now let's have another scenario where we've got more trials, and we've now got a sequence where we've got a positive trial, 3 negative trials are positive, then 2 negatives are positive, then 3 negatives, again with the same alpha and power levels. There, what would you think? How strong is the evidence for or against? It's worth having a think about that. In fact, the treatment is actually very likely to be ineffective given that sequence, because you have got power of 0.8, which means that if there really is an effect, you should see it on 80% of occasions, and you're well short of that. And so the evidence goes in the opposite direction. Now the key point is that the second sequence I gave you is really the same as the first sequence, but with a few additional negative trials. So one could say, well, in the real world, if you don't report negative trials, you can move from a scenario where you look as if you've got overwhelmingly positive evidence to one where really there is overwhelmingly negative evidence in the real world. If we don't report the trials that don't work, we can build up this impression that the intervention is highly effective. So in this graph now, we've just basically taken out all the blobs in here that are red that are pulling things down, and then you get that curve that will actually go up. It was realization of this sort of thing that led to the clinical trials field adopting trial registries and insisting that if you run a trial, it should be recorded somewhere that you have run the trial, so that people at least know whether there are trials out there. And you should also, on a registry, report the ultimate result, even if it's not published formally in a journal. So how common is it in practice that we see this kind of publication bias? Well, sadly enough, it's common even if there are trial registries. In fact, the fact that there's trial registries is what makes it possible for us to see this phenomenon. So here's a study that was done by De Vries and colleagues, who took studies that looked for treatments for depression and evaluated how effective they were. And if the study came out with a positive result, it's shown in green, and if it came out with a null result, it's shown in red. And the first thing you can see is that there are about half the studies that obtained null results did not get published. So that second set of bars is the studies that survived to get published. And even then, when a study got published, if it had a negative null result, it was more likely to be reported as if it was positive by somebody typically switching the outcome that they had decided to focus on, because they planned to look at one outcome, but then they found another outcome did give a different result. So you can see that that scenario I showed you of moving from a situation where it looked as if there was pretty good evidence, and then realising that if you put in the suppressed information, it's really very negative evidence, is very realistic. We do lose a high percentage of trials that are null results. So what can be done about this? We can try and exhort both authors and journals to publish null results, but there's great reluctance to do so because they're generally regarded as boring. So an alternative is to say we should adopt a different strategy and adopt a way of focusing on publications that is not affected by the actual results that you get. So Chris Chambers, who put forward this idea of registered reports back in 2014 and has implemented it very successfully initially in the journal Cortex, where he's an editor, and then in many other journals this model has been spreading. His key point is that the one thing that should not affect whether a paper is publishable is the results. It should be affected by whether you had a sensible question and whether you had a sensible approach to it methodologically and whether your analysis is appropriate. But the results themselves should be really pretty neutral. The results are the results. Yet they are what's affecting whether you get published. And his point is that this is very damaging because it's typical publication bias. So what happens in a registered report? Well, it's different from classic publishing in one key respect. So with classic publishing, you plan a study, you do the study, and then you submit it to a journal. And then you may have a long period of going round and round, getting reviewer comments, trying to address them, possibly resubmitting it to a different journal. And if you're lucky, at some point along the way, it's accepted and it's published, and you're very happy. Now, with a registered report, you have the same steps, but in a different order. So you plan your study, and then you submit it to the journal, the plan. That is reviewed. So the reviewers are not commenting on the study as it's done, but they're commenting on whether you've got a sensible question and whether you've got a sensible way of addressing it, a good, strong methodology, and an analysis plan that's likely to be conclusive in terms of showing you something. So that is then, hopefully, if you can satisfy the reviewers at that stage, you'll get your paper accepted, even though you've not yet run the study. And provided you do what you said you were going to do, then the paper will be published in the journal. So it's already been accepted in principle, as it's called. You might want to do other things than what you plan to do in the paper, but it should be very clear that what you've actually what you said you were going to do and how that relates to what you actually did. So the publication decision is just based on whether there's an interesting question addressed with strong methodology rather than on the results. There are other approaches. I'm happy to talk about registered reports. I've done a few of them now, and I'm a huge fan of this approach. I think it's great, but it's not always feasible. And a lighter touch, similar idea, but less compelling, if you like, is to just pre-register what you're going to do, but not have the peer review stage. So you actually deposit all your study plans and so on, and you can put them in various places. One is Open Science Framework, OSF. You then do your study and submit it to a journal, and then you have the usual round of reviewer comments. But at least there is a sort of hard record of what you plan to do, and that to some extent is positively regarded by many people as a sort of evidence that you haven't, for example, switched outcomes and so on. And similarly, there's another thing that you can do, which is to do the full study, but then have a journal that agrees to do what's known as results blind publishing, where they look at your study without the results section and on that basis decide whether to publish it. So again, focusing on the methodology and the question rather than on the results. And it should be the case that these sorts of approaches will reduce publication bias. The second reason why we have problems, though, I think, is not just publication bias, but also citation bias. This is the same De Vries study taken to the next stage. So they then looked at the way that studies are reported, whether they are reported accurately or with spin, and you get spin of various kinds where people will really argue, for example, that a treatment was effective even though it wasn't. But then the last set of bars is citation bias, and here the size of the green dots relates to how many citations there are to that paper. And this is really quite striking because you can see here that the little red dots there indicate the small number of papers that survived through to this stage. They got published, they got reported accurately and so on, but then they don't get cited. People are not interested in negative trials, whereas these positive trials get cited far, far more. So this is really a problem that's a different one to publication bias, but with a similar impact in that if you read a paper in the literature, you follow up on the things it cites, you're not going to be aware necessarily that there's negative evidence if they don't cite it. This rather complicated and difficult to read graph, I'm afraid, I took it straight from the article, is from an excellent article by Greenberg, who talked about what he called citation distortions, and again, create unfounded authority. Similar idea to this false canonization, this idea that you think there's a whole load of evidence supporting something, but actually it's smoke and mirrors. So he was interested in the hypothesis that beta amyloid is produced by an injured skeletal muscle of patients with a condition known as inclusion body myositis. And he was able to find a network of papers so that these papers cite one another, but 242 papers, 675 citations, and then he traced all these citation paths as to how each paper cited other papers. And he found strong citation bias against papers that didn't support the hypothesis. So what you can see here are lots and lots of black lines, so time goes up the y-axis here, and so what you would expect is that the later papers would be citing the earlier papers, but what is actually happening is that later papers do cite earlier papers, but only if the earlier papers agree with that theory. So there's a little cluster down there on the left, papers 70, 71 to 72, 73, 77 and 78, which are cited once, and these are a group of papers that failed to find support for the particular theory. So this really just shows how we will ignore things that don't support the theories that we like, and we will give the impression to anybody coming behind us and reading our papers that there's overwhelmingly supportive evidence. This is not perhaps as surprising as one might think, because it's part of how our brains are wired up to do something called confirmation bias. There's quite a big psychology literature on confirmation bias, which is really always showing that it's much easier to process and even remember information that agrees with our viewpoint. And I've got a personal instance of that in one of the papers in the reference list, where I talk about my own experience of completely forgetting a paper that happened not to agree with a case I was making until I was forced to do a systematic review and look at all the literature. So I'm quite sympathetic to the idea that this is often not deliberate. It's something that I think it's quite hard to resist. What are the solutions, though? Well, I think an obvious solution is to try and use systematic reviews rather than just cherry-picking bits of literature that you want to cite in a paper. And I think the case can be made for saying that graduate training should include a requirement to do a systematic review on a topic related to the one you want to work on. That's pretty tough. It's not a simple thing to do, and it takes time, but it would get you thoroughly immersed in the relevant literature, reading it in very much more detail than you otherwise might, and also might protect you from ending up being one of those poor people who's tried to build on something that really isn't very solid, make you much more aware of things in the literature that maybe don't agree with your interesting theory. Most guidelines about doing systematic review are coming from the field of clinical trials and are not always suitable for other types of studies, but I recommend this preprint by Jade Pickering and Marta Topor and others who have put together some guidelines for studies that don't involve intervention, but steps that you can follow if you want to do a systematic review. And we found that in our group very useful. And then the other thing you can just do is increase awareness of how serious it is to be somebody who contributes to bias reporting. I think a lot of the time we think of it as a sort of some sort of victimless crime. Does it matter if I don't cite this paper, but I do cite that one? But if you start thinking of it, how it accumulates and how people coming behind you may rely on your references in your paper to get an impression of how strong something is, this is all building to this false canonization of false facts. So it affects users of research and it affects other scientists. And many people who are training, I think these days, don't really get taught to adopt an appropriately sceptical attitude to everything that they do, even though that's been a core tenet really of good science for many, many years. And in fact, this term, organised skepticism, is one of the 4 norms of good science that was put forward by Merton, sociologist of science, many years ago, that it's this sort of mindset where you just don't trust things. You approach things with great caution. And I think we don't train that in people very often. It's more in some disciplines than others, but in some, science seems to be made to think that you're trying to prove your theory. You should actually be trying to look very carefully at it and find ways of disproving it. And there's some nice examples of famous scientists who make this case. I was really pleased to find this quote from Charles Darwin's autobiography, which just fitted beautifully what I was thinking about. And so he talks about how he followed a golden rule that whenever a published fact, a new observation or thought came across me which was opposed to my general results, to make a memorandum of it without fail and at once, for I had found by experience that such facts and thoughts were far more apt to escape from the memory than favourable ones. He's really giving a very nice early description of confirmation bias, this business that you just don't remember and process things that don't agree with your views. I like the last sentence as well, because he points out a real benefit to thinking this way. You might think, well, this is terrible, it's going to hold me up because I'm continually trying to think of negative things. But of course, you really need to be well defended against objections to your theory if you're putting it out in the world. And what he points out is that, owing to this habit, very few objections were raised against my views which I had not at least noticed and attempted to answer. If you yourself can be the first person to anticipate the objections and really deal with them, you'll be in a much stronger position when you come to, say, try and publish your work. You won't have referees coming up with things that you had failed to notice. This is another everybody puts this quote up because it's such a nice one, but it's from Richard Feynman that, the first principle is you must not fool yourself, and you are the easiest person to fool. And I recommend reading more of what Feynman's written on this, because he's very good on the whole idea that you need to be your own worst critic. You need to be really trying hard to break any favourite view that you've got and really put it up against really tough evidence, not looking for consistent evidence, but looking, on the other hand, for things that wouldn't fit. Okay, that brings us on to reason number 3. We're going to get a bit more statistical again, I'm afraid, but this is part of many scientific disciplines. I realise it doesn't apply to all, but those that use statistics in order to draw conclusions about whether evidence is fitting or not with a particular hypothesis frequently don't understand the statistics that they're using. And I think there's a lot of problem with how it's been taught as a sort of cookbook of formulae to many people, and people have a deep misunderstanding, particularly of probability, and this gives an excess of false positive results. So p-hacking is one of the terms that's been used to sort of search around in your data to try and find significant p-values. It's a recent term. It wasn't used in the 1950s, but it's very relevant to the work of de Groot, who did write about this failure to distinguish exploratory from confirmatory research, which is at the core of the problems with p-hacking. Interestingly, de Groot was very famous in the Netherlands and was a famous chess player as well as psychologist, but his work wasn't well known because it was written in Dutch, but it was translated in 2014 by E.J. Wagenmakers and colleagues, and it's a really great read and it's very relevant to today. But the key point he makes is that you obviously have to do exploratory research as a scientist. You're generating a hypothesis by looking at lots of observations and formulating hypotheses. But then you do a different type of research. You do confirmatory research to evaluate your hypothesis. And the real problems arise if you use the same data to try and both generate and test a hypothesis. The statistics no longer make sense. And it's very hard, people are not intuitive about this. It's quite hard to try and explain it. And I've tried all sorts of different ways, and some I think work better than others. This is one approach of why p-hacking is problematic, using poker. So if you've got those of you who are into poker will know more about it than me, but you get a hand of 5 cards, and these hands will have value in relation to how improbable they are. So games of chance were one of the earliest places where probability theory was developed, really. And there's about a probability of 1 in 50 that you'll get this thing called 3 of a kind, where you just, in this case, have 3 queens. And I imagine I've got a friend who thinks he's a great magician, and he comes into the room and he says, well, he can just, without cheating, deal 3 of a kind by forming some sort of mental image of it or something. And then he does so, and you think, wow, he's really got some magical way of controlling the card. If you're in a room of 50 people and he does this with everyone and only one of them gets 3 of a kind, of course you wouldn't be impressed. You'd think, he's doing no better than you would expect. I mean, every now and again you expect to get one of these hands, but he's really, there's nothing special. But the person to whom he does it thinks, oh, this is amazing, he's succeeded. So the problem is that you can't really interpret a probability without knowing the context in which it was obtained. So the probability associated with 3 of a kind is 1 in 50. But if he tries it out on 50 people and gets just 1, that's not impressive. If he were to do it into 50 people and all of them were to, or even half of them or a third of them were to get this, it would be very impressive. But this is the point. You need to take into account the context. Another way to look at it is to just simulate data. So here we have some data simulated just from a random normal distribution with a mean of 0. And each time take a little sample and plot the mean and standard error. And let's pretend that this is this is a study on a group of rats, and we're going to say that we think that we've got a whole set of compounds that we're screening to see if they improve the memory in rats. And then we get very excited because we see we've got 2 compounds, G and J, which are statistically significant and where the memory is better than you would expect just by chance. So you get excited and you think, let's develop further research on these. And this is a sort of thing that happens all the time. This is wrong logic, because if you're actually testing 16 compounds with no prior belief about which of those compounds may or may not be effective, you need to adopt a different approach to evaluating probability. We're not actually testing here whether J is significant. We're testing whether any of the 16 compounds is significant. And again, sorry, some horrible maths coming in here, but think about each of these compounds. What's the likelihood that it's not significant? Well, it's going to be 0.95 because you've got alpha of 0.05. So you've got a 95% chance that anyone is not significant. So what's the probability that they'll all be non-significant? Well, it's 1 minus 0.95 to the power of 16, which comes out as 0.6. So this is the probability, in fact, that you're going to find something if you do this sort of study. It's not 100%, but it's pretty high. So once you see that, you realise why it's important to correct for multiple contrast, which most people are taught to do, but a lot of people think of it as some sort of optional extra that's, sort of statisticians insist on because they're just being difficult. It's not that at all. It's absolutely crucial that one takes into account the number of comparisons. If you're testing in this unstructured way without prior predictions, you're testing lots of things. So p-hacking would be to pull out just those 2 results and not even report perhaps the others. And then it's very difficult to know that anything wrong has taken place because you've actually only got 2 compounds and they've both got these significant results. And you think, wow, well, this is the problem with the use of p-values, as if they are some sort of measure of effect size, which they're not. They're a measure that can only be interpreted in the context in which they were obtained. There's a related sort of type of there's many forms of p-hacking, and I haven't got time to talk about all of them, but there's things like you can look at subgroups, you can adopt different forms of analysis, you can decide to sort of stop testing at a particular point. There's all sorts of ways that you can sort of massage your data to try and optimize p-values. This one of shifting goalposts, I think, is very, very common in the literature on biomarkers, where people are looking for either genetic or neural markers of typically clinical conditions. And there's a sort of sequence of events that you see taking place over and over, and that is that you start with this big red star, you start with a very striking result that gets published. Grey blobs are studies that don't get published because they're not very interesting. So already you've probably got some capitalization on chance that this one study by publication bias got published. But that spawns a literature of other people trying to do the same thing. But again, you then have lots and lots of papers coming out, but many of them don't ever see the light of day because they obtain null results. So they're the little grey knobbles at the end of these. But the stars are the ones that find something, and then they will generate more. But typically, in a lot of this sort of biomarker area, what you find is that the original result is not what is being replicated here. People end up doing things that are similar but not quite the same. So, for example, they will then say, well, it worked in males but not in females, or that it worked in children but not in adults, or that it worked with this measure but not with that measure, or indeed that there's interactions between things. So it's broadly on the theme of that initial study, but with subtle differences. And the possibilities for p-hacking here are often immense. And so you get this completely fictitious notion that you've got this highly robust result because so many studies seem to find it. There was a very striking way in which this was blown up recently in 2019 in the case of a serotonin transporter gene, 5-HTT-PLR, LPR, and depression, where historically for many years people had been saying that they thought that there was associations and there were studies, literally thousands of studies published on this, either that there was a direct association or there was some interaction with this gene, until this paper was published in American Journal of Psychiatry with massive samples, good measures, good methodology, arguing that nothing replicated. And there was a very nice and quite funny blog post about this by Scott Alexander, who likened it to unicorns. So he says, what bothers me isn't just that people said 5-HTT-LPR mattered and it didn't. It's that we built whole imaginary edifices, whole castles in the air on top of this idea of it mattering. We figured out how the gene exerted its effects, what part of the brain it was active in, what sorts of things it interacted with, how its effects were enhanced or suppressed by the effects of other imaginary depression genes. This isn't just an explorer coming back from the Orient and claiming there are unicorns there. It's the explorer describing the life cycle of unicorns, what unicorns eat, all the different subspecies of unicorn, which cuts of unicorn meat are tastiest, and a blow-by-blow account of a wrestling match between unicorns and Bigfoot. So he's pretty sharp, and he's, like me, sort of pretty annoyed by the whole thing, because when you look, I don't know if anybody has done a sort of economic analysis of this, but if you were to add up all the costs of all the studies that have been done, it would be really massive amounts of research funding that have been dedicated to this. Whereas if from an early stage people had been a little more careful, a little more thorough, not sort of distorted the literature either with publication bias or with citation bias or with p-hacking, we could have really dismissed this one a lot earlier. But it sounded so good and people wanted to go with it. So what are the solutions to p-hacking? Well, interestingly enough, registered reports. They're great because they also, as well as avoiding publication bias, they make p-hacking visible. If you've committed in advance to say this is the outcome measure you're using, then it would be very clear if you did something different in a final paper. And indeed, you wouldn't get published, you wouldn't be allowed to publish that as part of your regular results if you had a registered report format. The other thing you can do, I think, that makes a big difference and makes people more aware of how serious p-hacking is to do, again, data simulation. I've mentioned it already, but it's very, very useful. I mean, this sort of little plot that I produce here can be very easily produced, and you can run and run and run something like this many times and show how on different runs different of these components would look significant, and on some runs nothing would look significant, and some you'd get lots popping up from exactly the same script. When you know, the beauty of simulation is that you know what is the truth, you know that actually there is no real effect here. So those two things I think are very important ways of potentially controlling for p-hacking. The other side of the coin is reason 4, and that is when you get inconclusive results because your studies are underpowered, and indeed you may miss real effects because you're not looking at them with sufficient statistical power. And people, again, massively underestimate how important this is, I think. They tend to think of statisticians who raise issues of power as killjoys because the statistician will almost always say you need a bigger sample than you can actually get. I want you to just sort of pause to think, if you were going to do an educational intervention, I realise many of you this is not your area, but suppose I said I've got a reading intervention, I'm going to boost children's reading, and it was a plausible intervention, what would be the likely effect size for something like that? There's been a lot of people pulling the literature together in the field of education, and the answer is you typically will get effects for a good intervention, 0.3 to 0.4. Of course, a lot of interventions don't work at all, so you get effect of 0. But there are some which seem to reliably give effects of that size. So the next question is, what would that look like if you plotted a treatment group and a control group? Of these three options, if I said to you, you've got an effect size of 0.3, which of those graphs would tend to characterise the distribution of the control group and the experimental group? Well, people are often quite shocked to find that the left-hand one is an effect size of 0.3, that one now in the top row middle. And it's really, you start to see that there's huge overlap between the two groups. And that is a typical effect size, that or even less, for things like sex differences in personality, effect size of 0.2 to 0.3, educational interventions 0.3 to 0.4, and quite a lot of medical interventions also. And it's only when you get to things like sex differences in height that you start to get these big differences that you can see with the eye very easily, where the two peaks actually separate out. So knowing about effect sizes is important, and people are often not really taught enough about them. So this relates to statistical power. So if you know your effect size, and we're going to stick here with one effect size of 0.3, how does that affect your ability to actually show an effect in an experimental setting? So I'm going to show you blobs here from a blue group, which is drawn from a population with a mean of 0.3, and a pink group drawn from a population with a mean of 0. But this time, the blobs are not actually individual people from those populations. These are estimates of a mean from a sample, and the size of the sample is shown along the x-axis. So it's quite complicated, but for example, on the left there, you've got two groups of 10, the pink group and the blue group, and we've just repeatedly ran simulations to pull out mean values for a pink group and a blue group. And what you can see is that the estimate of the mean, when you've got a very small sample, hops about all over the place. There's massive variability in that sample, because basically if you've only got 10 people in a group, one person with an extreme score is going to pull you way up. The more people you've got in your group, the more you see you get very reliable estimates, and indeed by the time you've got to two groups of 320 people, there's no overlap in those estimated means, and the blue group's mean is nicely close to where it should be, 0.3, and the pink group mean is close to 0. But people very much underestimate how variable estimates are in small samples and how much problems this creates. I've been trying really hard to find different ways of explaining power analysis, and I think this might hinder rather than help. So if you turn off at this point, don't worry. But I thought, well, it would be interesting to look at this thinking about log likelihoods. So the idea is that if you've got a small sample, and again, the number 10 should be right on the left-hand side there, but it's been chopped off. But basically, what I'm trying to show here is that if you've got a very small sample, even if you observe an effect size of as much as 0.5, you are not going to be certain whether it comes from a true a population with a true difference or no difference. That creamy area in the middle is what I call the zone of uncertainty. And that's just if you follow through those computations to get log likelihoods out, you only really start to get very strong evidence for or against a particular theory when you've got these larger samples. And then you see, so that the area which is shown in purple or in that sort of dark maroon colour are the points when an effect size with that sample size will give you very strong evidence. But as you can see, it takes big samples really before you escape from this zone of uncertainty. This is just a different way really of showing you power, but it's really just showing you that with small samples, when you see a particular effect, it's very hard to know how, it's just not very solid evidence one way or the other, unless you've got very big effect sizes that you're looking at in the population. So what are the solutions to low power? Again, I would say registered reports. So I keep coming up with registered reports because I think they fix a lot of the problems. Basically, they don't automatically fix this, but most journal editors, if they're going to be saying that they will accept in principle a study, provided you do what you said you were going to do, what they don't want to do is accept something that's underpowered and therefore, as I've just shown, inconclusive. So they will want typically for you to have high power, either 0.8 or in some cases 0.9, so that they know that if you run this study, you're going to have a good chance of showing an effect if it's really there. And registered reports also just encourage you to think about power and plan it into your study at an early stage. And again, data simulation is coming up again, because data simulation, if you're trying to understand power, what you can then do is to simulate data where you know, again, the truth, but the truth in this time is that there's a real effect. And you're going to therefore be able to see how, when there is a real effect, how often can you actually detect it. And I've run courses where I've done this with people, and they are usually incredibly shocked at how difficult it may be to show a real effect when you've got a relatively small effect size. Now, the problem, of course, with power is that sample size isn't the only thing that determines power, and it's important to bear in mind you can sometimes improve it by having a better design or better measures. But sample size is often a major factor, and it can be hard to achieve an adequate sample size to get a well-powered study. And this is where the current research ethos is very much moving towards saying, let's do collaborative research. Let's get several groups coming together to try and tackle this question. If you've got an important question and a good design, it's worth doing a study that's big enough to really show a result. And there's a lot of movement towards encouraging this, both between different research teams or even getting student projects to work as a team to do a large enough study to give sensible results. So I think, and of course collaborative research has other benefits in terms of there's more eyes on everything. Things tend to be done more carefully if they're done in collaboration and more thoughtfully. So that's another sort of way of thinking about dealing with power problems. Right, I'm come to the final one of my list. I'm sure I could find some more, but I think we're all beginning to run out of steam if we go on too much. So last thing, this is now a top-down thing. So we've been talking a lot about training researchers, things that researchers themselves can do. But of course, researchers are really influenced very heavily by the incentive structure that they work within. And we've talked already about journals who tend to reject things that are really non-significant. But there's also the obsession of both funders and journals with novelty. So I have been funded by Wellcome Trust and by ERC, and I love both of them for funding me so generously. But they both sort of have tended to have this attitude that if you're putting in a proposal, it has to be groundbreaking. That's the ERC's wording. And Wellcome sort of say, well, is your proposal just a direct continuation of existing work? That just, I feel, is not always appropriate, because sometimes if you've done existing work, you want to continue it because it's going well And if you look at the careers of many Nobel laureates, they did a continuation of existing work for 10 years, 20 years before they got to the bottom of things. So I think, there's a little bit of, we've moved too far in the direction of thinking that novelty is wonderful. Of course, nobody wants to just do pedestrian, boring, pointless things. But if the question is good and you've got a good way of addressing it, I think the fact that something is something you've been working on already should not be held against you. In fact, I wrote a blog post about this, where there's this sort of notion of things have to be groundbreaking, novel, transformational. I think it can actually be an enemy of this high-quality cumulative science, because what tends to happen is that you get people who've so much focused on novelty that, like this frog sitting on his lily pad, they do something, they publish a paper, and then they hop off to another lily pad and do something rather different and hop off. And it really doesn't help, because they tend to not be invested enough in any one thing to really see it through. This is often encouraged, of course, by short-term funding, because if you've only got 2 or 3 years worth of funding, you're often looking for the next thing while you're working on one thing. So it's often because of top-down influences, but it's problematic. Now, I see cumulative science as something that should be more like this fine termite mound, where the researchers are like the termites and are working together, working collaboratively, and building something, literally sort of building things on top of what has gone before, in a much more structured way. So this notion of accumulation is something that I think has to be very central to what we're doing. What are the solutions? Well, I think the solutions are on their way already, because I think what has become very apparent in recent years, and it's some of the funders have clearly got this message now, is that they're in danger of wasting their resources. So I mentioned that thing about depression and serotonin genes. What a waste of resources, having people going on and on and on, all trying to do something novel, but really never actually checking that the original finding is solid. So you need to be spending more time doing cumulative stuff properly, and I think that has been a lesson to some of the funders, that they've wasted resources. And they're also concerned that if people are continually told that they've got to get things out in top journals and they've got to be very novel, they will cut corners and they will overhype research. And ultimately it can even be an incentive for fraud, which I won't talk about much today, but it is a worrying problem in some corners of literature. And then you could end up with a situation where people who really can see what's happening and realise how damaging this is, if people are being encouraged to adopt sort of quick and dirty practices and not do things properly, they will just be disappointed and leave. So we're losing the people who have the most integrity. And I think these messages are beginning to get across. I was really pleased to see this article by Ottoline Laser, who's the chief executive of our main funding body that oversees all the research activities in different disciplines in the UK. And she's always said things that I thoroughly agree with. So the excessive focus on the publication of groundbreaking results in prestigious journals. Science cannot only be groundbreaking. There's a lot of important digging to do after new discoveries. But there's not enough credit in the system for this work, and it may remain unpublished because researchers prioritise their time on the eye-catching papers hurriedly put together. Very much in line with what I've been saying. That, and in fact, she's got a very nice quote somewhere else where she says, if everything's groundbreaking, you just end up with a lot of holes in the ground. So I thought it was a nice way of putting it. But things are changing, and I was really pleased to see this last year, the Hong Kong principles for assessing researchers, which are the idea that we need to have different principles. We should stop evaluating people in terms of how many papers they have in high-profile journals and how much grant income they bring in, but we should start actually giving people credit for research integrity and for doing research carefully and well. And this is already not very readable, and the original was even less readable, and I won't go through this in detail, but this is in that paper, this whole model of the things you can start trying to evaluate rather than the sort of metrics that we've currently relied on. So are people using open protocols? Are they pre-registering? Are they sharing their data, their materials, reusing data from others? And then there's another load, are they sharing their code? are they working transparently with open access, using reporting guidelines, and so on. So this could be a whole hour talk on its own, but I wanted to just put this up to encourage people to be aware of how much this space has moved very, very quickly just in the past 10 years or so. I think that there's been a dramatic change in attitudes towards all of these things from people whose main goal is to feel we've got to improve science. And so I've got some references separately that I think will be made available to you. And otherwise, I think it'll be great to just spend time having some questions with you.